In this video, you'll see how the Newton-Raphson method of finding roots of functions can be used to generate fractal patterns. It involves calculus, but you don't need to know anything about calculus. However, you may remember some algebra from high school, in particular about finding the roots of a function. That's where the graph of the function crosses the x-axis. For this cubic function, you can see the roots are -2, 0, and +2. But you rarely have a graph to see the roots, and so you have to solve them algebraically. Isaac Newton, along with Joseph Raphson, came up with a nice way of finding roots. We're going to use their method to generate fractals. First, we'll see how this algorithm works. We'll use that same function to illustrate the method. The first step is to pick any initial value along the x-axis. We'll call it x0. We calculate the function value at that point. This gives us a point on the curve as shown. Next, we draw a line through that point that is tangent to the curve. This line crosses the x-axis at another point. We'll label this point x1, and as you can see, this gives us another point on the curve. Now we draw a tangent line through this point. Notice that it crosses the x-axis at yet another point. Let's call this point x2. If we continue this process, we will get closer and closer to the root x is equal to 0. Suppose we started with a different x value. As before, we call it x0 and draw the tangent line at the corresponding point on the curve. As before, this tangent crosses the x-axis at another point, say x1. Continuing the process, we get another point, x2. Ultimately, we will converge on the root x is equal to -2. Notice that different starting points can produce different roots. Continuing with this example, suppose that we chose the initial point anywhere on the two-dimensional plane. Using the x value of this point as our initial x0, we see that the process continues as before. Any starting point on the dotted line will produce the same root. All of this suggests that we could choose every point in this area as our initial point and find out which root it converges to. If it converges to the root x is equal to -2, color it orange. If it converges to 0, color it green. If it converges to x is equal to +2, color it blue. Let's do this now. And here is the result where we colored each point according to which root it produced. For example, you can see that every point appearing in orange converges to the root x is equal to -2. No matter how complicated our function is, it will always produce vertical bands of color. This isn't very interesting, so let's move over to the complex number plane. Without going into details, let me say that multiplication of complex numbers behaves differently from that with real numbers. So the Newton-Raphson algorithm produces different results. Instead of vertical bands of color, we get interesting fractal patterns. Here are some sample functions we could use. Notice the one-to-one relationship between the highest exponent in the function and the number of roots it has. Suppose we have a given function like one of these. We know how many roots there are, so we assign a different color to each root. Using every point in our subplane as our initial point, we use the Newton-Raphson method to find a root. Then we draw that point in the color we assign to that root. I think it's time for an example. This function has a highest exponent of 7. So we assign 7 different colors to the 7 roots. Here is an example with 10 roots. And this function has only 3 roots, so only 3 colors were used. Not quite as interesting as the function with higher exponents. We'll use this example, which has 11 roots, to illustrate the fractal nature of these images. We'll zoom in on the image to see how the patterns are replicated. Hope you enjoyed that.